have been discussing in the last class. So we were talking about the Doppler velocimetry. We said that the Doppler velocimetry basically works on the principle of incident wave and scattered wave, which interferes with a particle moving along with the flow. And it is assumed that the particle moves at the same velocity as the fluid. So we said that if we have a particle here inside the fluid, and this is an incident wave at certain frequency and certain wavelength, because of the presence of the particle, this incident wave is scattered. And when the wave is scattered, its wavelength remains unchanged. And the frequency changes. The scattered wave is collected using a detector at an angle theta with the direction of velocity of the particle. So you can always have the component of the velocity along the incident wave as well as along the scattered wave. So if you take a component of the flow velocity along the incident wave, it is going to be 0 because the angle is 90 degrees. But that between the flow velocity and the scattered wave is theta. So the component of flow velocity along the scattered wave is going to be v cos theta. So you can actually find out the frequency of both incident wave and scattered wave. The frequency of incident wave is nothing but the velocity of a sound, that is c in that medium, divided by the wavelength of the wave. But if you talk about the scattered wave, there is a change in the frequency. That is going to be the speed of sound, speed of wave, plus the component of flow velocity along the scattered wave, that is v cos theta, divided by the wavelength lambda. So there is a change in the frequency that is known as Doppler shift or Doppler shift frequency. And this is the new frequency minus the initial frequency, which is c plus v cos theta over lambda from here, minus c by lambda. So that is v cos theta over lambda. Now, there can be situation where the incident wave will be normal to the flow velocity direction. So for example, here, so you have a particle here which is moving at velocity v along the direction of flow with the same velocity as the fluid velocity, that is v. The incident wave is making an angle theta subscript I with the flow velocity. And the scattered wave makes an angle theta subscript s with the flow velocity. So as I said, v can have a component both along the incident wave as well as the scattered wave. So this v can have a component in this direction, right? That is the incident wave direction. This angle is nothing but theta I. So you have the incident wave frequency as from here, it will be c plus v cos theta I minus lambda. And the scattered frequency is going to be c. Then you have v cos theta s over lambda. So if you want to know the Doppler shift, you do the difference between the two, which is going to be v by lambda into cos theta s minus cos theta. So from here, you can see that Doppler shift occurs only if the particle has non-zero velocity. If v is 0, there is no Doppler shift between the incoming and outgoing frequencies. Okay. And the other thing to learn here is the Doppler shift is proportional to the velocity of the fluid. Okay. So that means if you have an instrument which can measure the Doppler shift or the change in the frequency, and we know the position of the transmitter and the receiver with respect to the flow direction. That means if you know these angles, we should be, and we know, of course, know the wavelength of the signal that we are giving it to the system. We can predict what is the flow velocity. So we talked about the construction of this ultrasonic Doppler velocimeter. So typically, this is what is done. So you have a tube in which we have flow velocity. Fluid is moving at some velocity v. So we have a opening in the tube here where we mount the transmitter. And then we have another opening here where we mount the receiver. So we precisely know what is the direction of the incident wave and the scattered wave with respect to the flow direction. This is coming from geometry. So we said that the transmitted wave can be a can be represented with by an amplitude and an oscillatory component, which is given as cos omega t, omega being the frequency of the incoming signal. And the scattered wave would typically have a frequency shift, that is, of course, it will have an amplitude. It will have a frequency shift, that means it will be omega plus omega d, t should be outside the bracket, and it will also have a phase shift. Now, if you have the transmitted wave known by a control system, and the control system also knows the scattered wave, it can perform multiplication of the signals using the signal circuit. So it can say ut into ur, the transmitted and reflected signals are multiplied here. So when you multiply these two, this is what you get. And using the trigonometry identity, we say that cos A into cos B is half of cos A plus cos A plus B minus cos A minus B. So this will give you this formula as we discussed. So you can see that the signal now has a high frequency component, that is omega is very high frequency component. Omega is typically smaller. That means the Doppler shift frequency is typically smaller than the incoming frequency. So you have a high frequency component and then you have a low frequency component. Now, typically, our objective here is to measure WD. So we need to somehow take out this incoming frequency and from the signal, and so that we only get WT. And once we get the incoming wave frequency using this formula, we know the geometrical parameters, so we can predict V. So that is what is done by this circuit as we discussed. So we have, this is the resonator, so which basically feeds the signal to the transmitter. And after scattering, the receiver actually receives the signal. And this signal is typically weak, so it is amplified. And then this amplified signal is basically demodulated. That means you separate out the high frequency and low frequency signals. And here, for the low frequency signal, you ensure that there is a threshold. And once it is above a threshold, you basically consider the signal. And then you have a multiplier for the low frequency signal. And then you have a low pass filter, which basically subtract the high frequency signal and only have the low frequency signal. And that means the output here just gives you the low frequency signal with the corresponding Doppler frequency. And this omega d is known, from which the velocity is calculated. Now, we can have a different setup, which is known as ultrasonic flow meter. So the principle is that when you have a pressure disturbance in the fluid, which can arise from ultrasonic actuation, and this ultrasonic actuation, ultrasonic crystals are such that if you apply some electrical voltage, they will oscillate, and these oscillations will send out pressure waves. So these pressure waves basically are sound waves, and they can travel at the speed of sound. And if the fluid is flowing, then the depending on the direction of the fluid flow, then the net velocity of the sound will either increase or decrease depending on the relative directions of the sound wave direction and the fluid flow direction. So typically, the ultrasonic waves have frequency of the order of 1 to 10 megahertz, or it can be even higher, so up to 100 megahertz. And these sound waves are typically generated using a ultrasonic crystal, okay, which is basically the transmitter. And it is basically collected by a receiver, okay. And depending on the location of the transmitter and receiver, the time of travel of the signal would vary. Okay, so for example, this is the tube, and this is the flow direction from left to right. Here is the transmitter, here is the receiver, and this transmitter basically is sending out the sound wave signal at a velocity v subscript s is the sound wave velocity. Now, since there is a flow velocity, these two superimpose. That means the sound wave travels faster at a velocity of Vs plus the flow velocity. And let's say the distance between the transmitter and receiver is L. Okay. So we can say that when there is no flow, when V is 0, your time that the sound wave takes to reach the receiver from the transmitter is simply L divided by the velocity of sound, right? And now if the fluid is moving at some velocity V, then the transit time is going to reduce, and the transient time is going to be L divided by Vs plus V. So you can do some mathematical adjustment. You can multiply by Vs minus V on numerator and denominator. So this becomes L into Vs minus V divided by Vs square minus V square. Now, these flow velocities that we typically encounter in practical systems are much smaller than the sound wave velocity. So sound wave moves at, let's say, in water at about 1500 meter per second, right? And the flow velocity that we measure, typically maybe a few meter per second or maybe tens of meter per second, but way below the sound wave velocity. So when V is very small compared to Vs, V square will be even smaller. Denominator can be simply approximated as Vs square. Okay. So you have Vs square here. So L over 1 of the Vs here will give you T naught, right, as per here. And the other Vs will divide with this. That means it will become 1 minus V divided by Vs. So this is what we get here after making an assumption that the flow velocity is much smaller compared to the sound wave velocity. So you have T equal to T naught into 1 minus V by Vs. So you can see that this time of travel of the signal in a flow system is a function of the flow velocity, the sound wave velocity, and the zero flow transit time, T naught.
Sir, I have a query over here. Can I ask? Hello?
Yeah.
Sir, there's the flow, the sound wave velocity that will be dependent on the medium in which the sound is being transmitted.
Exactly.
So suppose, sir, if while the measurement is being done and the field temperature of the flow is changing, suppose, then the velocity of sound will vary. because density will change.
In case of liquids, the sound velocity with temperature is not very strong. But in case of gas, there is some change that happens. Of course, I mean, if there is a change in temperature, there is a change in density, and more for gases. And if there is a change in density, there will be a change in velocity. So those effects have to be accounted by the control system. If there is, so there has to be a simultaneous measurement in temperature, which should be considered by the control system to account for the increase and decrease in the sound wave velocity.
Right. Thank you so much.
So even from here, the you can measure T, and if you know the velocity of sound in the medium, you should be able to predict V. But what really happens is that measurement of this T0 is very difficult. Why? Because when you have this separation distance, let's say of the order of centimeter or even meter, you can see that the time it takes to reach from the transmitter to receiver is very small. Okay, so you can see that if it is L is of the order of a meter, and this is about 1500 meter per second, this will be of the order of millisecond or smaller. So measuring this time with reasonable accuracy becomes tricky. Okay, so this is one of the limitations of this kind of arrangement. So there is an alternate arrangement which is proposed, so where you need not, have to calculate the T naught, that means the zero flow transit time. So here you have two sets of transmitters and receiver. So let's say flow is in this direction from left to right. So you have a transmitter, in one case, you have a transmitter at the left and the receiver on the right. That means the sound wave is allowed to move from left to right. But in another case, you have the transmitter on the right and receiver on the left. That means in this case, the sound wave is moving opposite to the direction of the flow. So we can actually, determine the velocity using this method, which is called travel time difference method. The previous method was called single receiver transmitter system. So one transmitter, one receiver. Here it is called travel time difference method, where in the first case, when you have transmitter here and receiver there, you find the signal travel time as L divided by Vs plus V. In the second case, you find out the signal travel time as L divided by Vs minus V, right? So if you measure these two times using a control system, you have an appropriate clock to record these times. And also take a difference between these two signals, T2 minus T1. Then it is going to be, you can find out T2 minus T1 is going to be 2 into L into V divided by Vs square minus V square. Okay, so these denominators you take common, and this will be LVS minus LV. This will be LVS minus LVS minus plus LV. There will be 2 LV divided by VS square minus square. Now, as we discussed, this flow velocity is way smaller than the sound wave velocity. So you can approximate this by neglecting V square here. So essentially, you will have 2 into L into V divided by Vs square. Okay, so that means if you know the time difference between the travel time of this signal in these two cases, that means you are able to measure delta T using a control system, and you know the length where they are located, you know the sound wave velocity, you should be able to accurately measure the flow velocity. Okay. So there is a third arrangement that we see here, and this is known as oscillating loop system. So here, as we rightly said, that the sound wave velocity measurement can sometimes influence the data. So let's say you do not know the sound wave velocity, then what do? Okay, there you have a fluid for which Vs is not available, or let's say Vs is changing. So you can use this kind of arrangement, and this is known as oscillating loop system. Okay. So you can see that you have a transmitter, you have a receiver, and in this case, the flow direction is left to right. So you have Vs plus V is the velocity of sound wave. Is transmitted from here and received here. And once this transmitted signal is received, okay, it is received and then amplified. And this amplified signal and again fed back to this transmitter. Okay. So you can see that this goes in the loop. Okay. So the pulse that is transmitted by T1 is received by R1, but then after some time, this received signal is fed into the transmitter, and then again this is retransmitted. And then again this retransmitted signal is collected and amplified and then fed. So this goes in a loop. Okay, so that means at the receiver end, you will have a train of signal collected. At the transmitted end, you will have a train of signal emitted. Okay, and this train of pulses that are generated are related to the time period of the travel of the waves. Okay, so that means these signals, the train of signals that are received or are transmitted, will be separated by the travel time of the wave from the transmitter to receiver. Okay, so the travel time, as we already know, is L divided by the separation distance divided by Vs plus V. Yeah. So if you know the travel time, the repetition frequency, that means the frequency of the receipt of this pulse signal here, or the pulse transmitted signal here, is basically inverse of this time. Okay. And for example, you take 5 seconds, just for an example, if it takes 5 seconds for the signal to go from here to here, that means you are receiving every signal after each of 5 seconds, right? After every 5 seconds, you are receiving signal here. And similarly, after every 5 seconds in a closed loop, you are transmitting signal here. So that means the frequency of transmission or receiving signal is 1/5 hertz, right? So similarly, the repetition frequency will be Vs plus V divided by L. And you have the second case where the sound wave is moving from right to left in the opposite direction of the flow. So there, your repetition frequency is going to be Vs minus V over L, right? Now, you have a control system which can very well take the difference between these frequencies, repetition frequencies in both these cases, F1 minus F2. And as you see from the mathematics, Vs plus V divided by L minus Vs plus V over L. So that will give you 2V over L, right? So you can see, like, unlike the previous case where you had to know the velocity of sound, in this present case, when you are just measuring the frequency difference, Vs is out of picture. Okay, just by measuring the L, you should be able to predict the velocity. And as you see, the velocity of flow is proportional to the repetition frequency, the shift in repetition frequency, and independent of the velocity of sound, Vs. So let us then talk about electromagnetic flow meter. So this is the schematic that explains the construction of a electromagnetic flow meter. Typically, you have a tube through which the flow is happening, and that is shown here. So this is the cross section of the tube, and this is the direction of the flow. Typically, in an electromagnetic flow meter, you have a set of magnets diametrically opposite arranged around the tube or the pipe. So one magnet, which is the south pole, is at the top, and another magnet exhibiting the north pole is at the bottom. Okay, so you have north and south. North is at the bottom, south is at the top, around this pipe. Now, perpendicular to the direction of, so you have, when you have north here, south here, the magnetic field lines will go from north to south. Okay. Now, perpendicular to these magnetic field lines, you locate these electrodes. Okay. So the electrodes, the front electrode is here, the back electrode is there. Okay. So the line joining the electrodes are orthogonal to the direction of the magnetic field. Okay. So the principle is that it is basically based on Faraday's law. So you have a magnetic field that is established, and if there is no flow, the magnetic field lines are straight. When there is flow, the fluid basically cuts through these existing magnetic lines. Okay, when the fluid flows, the magnetic field lines get disturbed. Okay, and it is basically the Faraday's law. This is the direction of motion. This is the direction of the magnetic field. The third direction would give you the direction of EMF, electromotive force generated. So when there is flow, the fluid cuts through these magnetic lines, disturb the magnetic lines. So hence, there is electromotive force, EMF, generated across these two electrodes. Okay, and this induced electromotive force or the voltage has been correlated in this way. The electromotive force of the induced voltage is basically the product of magnetic field density, and the unit of that is Gauss, and L is the length of this fluid layer, that is, which is taken as the inner diameter of the pipe, and V is the velocity of the liquid flowing through the tube here in the unit of centimeter per second. And given these units, the corresponding voltage will have a unit of volt. Okay. So essentially, your induced voltage is in terms of flow rate, you can write in this way. The E will be 4 into B divided by pi d into Q into 10 to the power minus 8 volts. So you can see that your induced voltage is directly proportional to the flow rate. Okay. So if you have a given setup, given set of pair of magnets, you actually know what is the magnetic flux density. And the fluid is flowing through a given tube. That means you know the diameter of the tube. Okay. So with all these known, as you measure the voltage, the output voltage, the flow rate is linearly correlated. So by measuring voltage, you should be able to just directly predict what is the flow rate. Okay, so having discussed magnetic flow meter, let us talk about laser Doppler velocimeter. This is also known as LDV system. So this LDV or laser Doppler velocimeter system can be used to measure velocity at various points in the flow field. Okay, unlike this magnetic flow meter, electromagnetic flow meter, where you get an average information, right? The average velocity V is not at a point, but basically the average. Similarly, here in ultrasonic flow meter also, V is an average velocity. Okay, we don't get point information here. But laser Doppler velocimeter, which works based on the principle of laser beam, can really measure velocity at a point in the flow field. At different points, you can actually measure velocity, and you can create a velocity map, the variation of velocity at different points in the flow field. So you basically use laser, okay? And the advantage of using laser is that you can actually focus these beams to a very small volume, okay, thereby measuring the velocity truly at a point, okay. And this laser beam, which is focused at a point, would have very strong energy level. That means when you have let's say, a particle inside the flow, they would emit a very strong scattering signal. Okay, and this scattering signal is typically then can be measured with the appropriate optics. Okay, because scattering signal will be strong, then it has the advantage that the signal to noise ratio will also be good. And you actually use an optical detector system. For example, one kind of optical detector system is called PMT, or photomultiplier tube. So this PMT is basically, their purpose is to collect light signal and convert it into electrical energy. Okay, that is the purpose of photomultiplier tubes or PMTs. So what happens really is that you have a laser, okay, and this laser generates a beam, and this beam gets splitted, right? This is a beam splitter, and one beam just moves straight and falls on this lens. The other beam goes perpendicular and gets reflected at this mirror, and again falls on the lens. And these beams are then basically allowed to intersect at the point at which you want to get velocity information. Okay, and by adjusting the position of the lens or the position of the mirror beam splitter or the laser for that matter, you can adjust the position at the point at which these beams would intersect. Okay, and when these beams intersect, there is very high energy here. Okay, now when you have a particle in the fluid, okay, so like the Doppler method, the ultrasonic Doppler method, here also you need a particle in the flow field. If there is no particle, then there is nothing to scatter. That means this method is not going to work. Either you use some kind of impurity that is there in the fluid, or you introduce particles into the fluid. Okay, and these particles that are put into the fluid is known as seed particle. Seed particle means they are basically very small, and they do not influence the original flow field. They're not so large, or the concentration is not very high that they would change the properties of the original flow field. So these are called seed particles. They're very diluted concentration and very small in size. So when this particle crosses this point of intersection of the beam, where there is high energy, it actually scatters this laser beam. And this scatter signal is then focused using an aperture, and further by a lens, and collimated at the detector, which is a PMT or photomultiplier tube, as I said, which quickly converts this light energy that is falling into electrical energy. Okay. So since the scattering signal is appreciable, the falling light intensity is appreciable, the electrical signal, the corresponding electrical signal is also appreciable. Now, here, there are two light beams that are interfering. And as we know from optics, when you have two light beams intersecting, you have basically a fringe system. Okay. You have alternate peak and valley and peak and valley. So you have a peak system, fringe system that you have here when they are intersecting. This particle is basically perturbing this fringe system and scattering this signal in terms of a disturbed fringe that is appearing in the electrical signal there. So what you see here is this signal is basically the burst signal, because it is fringe. That means you have alternate high and low energy distribution, especially when the particle scatters. In the PMT, you also get this burst signal, which is oscillating in nature. Okay. And if the particle is moving at some speed v across the fringe system, and let's say if this fringe system has the spacing between the adjacent fringe is d, then the frequency of the burst signal is given by v divided by d. V is the velocity at which the particle is crossing. D is the spacing between adjacent fringes. Okay. So this is the frequency of this signal that is collected by the PMT, considering D is the spacing between these two adjacent black lines, and V is the particle velocity crossing the beam. So here, if lambda is the wavelength of the light, and if theta is the angle between the two beams, then this D fringe spacing, again from optical theory, is characterized as the wavelength divided by 2 sine theta by 2. That means if we know the angle of intersection theta, and you know the wavelength of this light, you can predict what will be the corresponding fringe. Okay, so that will be wavelength of light lambda divided by 2 sine theta by 2. So when you substitute this here, you get that, and you adjust the terms, you can show that V is basically F lambda divided by 2 sine theta by 2. Okay. And you can see that, okay, theta is a geometrical parameter that you would know. Lambda is, you know, what kind of wavelength, you are generating from the laser. Okay. And typically hundreds of nanometer. and your frequency f of the signal can be detected using the photomultiply tube, right? As the signal is coming, the PMT would show this oscillatory trend. Of course, I mean, this once you get the signal can be filtered into an appropriate signal here, starting basically the zero threshold you change, and you can appropriately make it as it's shown in the filter signal. And from here, you basically know what is the frequency, because you know the time period, you know the frequency, you know the lambda of the incoming wave. So you can predict the flow velocity. So here, just an example. We have, let's say, the wavelength of the laser is, let's say, 680 nanometer or 0.68 micron. And we know the velocity of light, which is 3 into 10 to the 8 meter per second. And these beams cross, let's say, at a 10-degree angle. Okay, this is a geometrical parameter, and you have defined this. Predict first the fringe spacing. The fringe spacing for this laser will be 0.68 divided by 2 into sine theta by 2. So that will be 5 degree. And that is basically 3.9 micron. So that means the spacing between between the fringes is basically 3.9 micron. And if that is 3.9 micron, if the velocity of the particle is 10 meter per second, then the burst signal frequency, the frequency of this signal, is going to be typically 2.5 megahertz. Okay, so it just gives an order of estimate of what kind of frequency of this signal that you expect. Okay, so but in a practical measurement system, this is what you would measure using the signal that is coming from the detector using a control system, and the velocity is something that you would predict. Okay. So let me stop here, and if you have any questions,
recording stopped,
we can discuss.
Sir, am I audible?
Yes, yes.
I'm just checking some applications of this LDV based systems. It is showing that we use it for some fuel injection velocity measurements also.
Yeah, yeah. So this is varied application. I mean, starting from aerospace, automotive, healthcare, many places LDV systems are used. Okay, so wherever you are interested to know the velocity of fluid, you can use this system.
So the sensor would be very compact in that case if you are measuring at that area.
Sensor has to be very compact. Yes. So the PMTs are actually, they are available of various sizes, and starting from, few centimeter by centimeter to millimeter by millimeter. PMTs are available.
Okay. Okay. Yeah.
Of course, you need to build an optical system around the flow path. You need to have a compact laser. I mean, this mirror and beam splitter lenses could be very, very, very small depending on the application. Okay, so if nobody has any question, then let us meet tomorrow again around 6 o'clock. Thank you very much.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, Professor, sir.